All right, cool. All right, this is Codecs and funny looking functors. Who am I? Vincent Marquez. That's my GitHub and Twitter. So if you want to argue with me about this stuff, follow me. All right. Currently working at Verizon Labs doing Scala. So if anyone's interested in working with me doing pure FP in Scala, definitely come chat afterwards. All right. Alternative title talk. Building real-world applications with FP libraries. So the last couple talks I did were kind of more theoretical. This is where I want to get into the weeds of showing how do I actually write functional applications in Scala. And we're going to touch upon a few theoretical ideas, but I want to show how we're going to do real-world applications. So the outline's kind of an introduction to Codec. So if you guys already know that pretty well, tune out for a bit. I'll wave my hands when it gets really interesting. I'm going to show kind of a real-world example of how I'm using this at Verizon. And also I kind of have a sample program to play with that I put up on my GitHub. We're going to get to NIO and more Functor stuff. And then maybe I'll try some live coding. Maybe. All right, what's Codec? Scala library for working with binary data. It's authored by Michael Pilquist. That's the website. It has a ton of documentation. So what's Codec? Codec is encoders, decoders, and together a codec. Basically a way to spit out binary data, read in binary data, and a bunch of built-in codecs for working with primitive types that you can compose to make a more complicated codec. So an encoder. It takes an A and it spits out some binary data. In this case, Codec uses bit vector to represent binary data, but it's just binary data. A decoder. It takes binary data, consumes some to construct an A, and also returns the remainder. But what does that mean? I'll show a more detailed example in a bit. Right. Let's look at some Scala. So this is an encoder. As I said, we take an A and we produce some binary data. Now, attempt is just a try. Like if you guys are familiar with try in Scala, it's a way to say maybe this worked or maybe there's an error. And it's a monad. But it's basically just saying whether or not we succeeded or not. All right, we have a decoder. A decoder, as I said, takes binary data, in this case bit vector, and then it has an attempt, whether or not it succeeded or not, and it gives us a decode result. Well, decode result, as I said before, is the thing you decoded, because you just did it successfully. It's inside the attempt. So you got a thing, but you may not have consumed all of the binary data that you're reading, right? If you're just going to get like a single int from 8 bits and you pass in, 128 bits, it's just going to take 8 and return the rest. So that's your remainder. So let's look at a really simple example. This is one of the built-in codecs that Codec provides. In this case, UTF-8. And it's going to be pretty simple. It's going to give us an attempt, which is successful. That's the success clause of a bit vector. And you can see the hex value of these 2 bytes, right? 68 is H and 69 is I. So you spend a lot of time looking at hex if you work with Codec. All right, let's see what happens when we decode. So what am I doing? I'm constructing a byte vector and then going to a bit vector just because it's easier to do this. But I'm passing in this value, 68, 69, to see what we get. We get a decode result of successful that has the high string, which is our A in this case. And it just grabbed the whole thing. It was, so 2 bytes. Here's another one. Uint 8. I bet everyone knows what it's going to be before if they looked. Right? It's 1. Pretty basic. All right. Combining them together. If we have a decoder and we have an encoder, we have a codec. So that gives us this encode function that we had before, decode, whole thing's a codec. So we have one single way of spitting data out and reading data in. All right. That's not very interesting because we're not going to be passing just like a string across the network or saving it to a file. We have to make something more interesting, right? So how do we combine these primitive codecs into something more interesting? So I'm going to kind of use the standard user fake example, right? It's got 3 fields, age, first name, last name. All right, we want to make a codec for this. So scodec gives us this : operator that's really just taking these codecs and making a tuple. Think of it as a tuple. It's really an H-list. But if you guys don't know an H-list list, it's a tuple of different types of codecs that we can then turn into a codec for a tuple or for a case class that matches the types of what that tuple would be. So this is going to give us a codec for user. Now we're going to encode our user, and we get 24 bits. Does anyone see a problem, though? Any guesses? Yeah? All right, let's see what happens when we decode our user. Right, I'm going to encode it, and then I'm going to flat map on it. Right, so this I want to make sure we understand. My encode returns an attempt, so I'm flat mapping on that. So I'm passing in a function that consumes a bit vector and returns an attempt of bit vector and flattening it. So we're going to see our result. What happened? She saw it. We got HW in the first name, and we don't have anything in the last name. So that's a problem. It's called the greedy codec. It reads all the bits. So that's not going to work when we were trying to size some of these things, and we want to make sure that a string only has a certain length. So let's solve it with a custom codec. We don't actually have to solve it with a custom codec because scodec gives us a sized string codec, a way to derive a sized string codec. But that's boring. Let's solve it because it'll show some cool concepts for how we can construct our own stuff. We're going to call it Var Encoder. So it's going to derive a codec from 2 other codecs. The first one is going to represent the sizing codec of the length of whatever our other one produces. So if that sounds confusing, it'll make more sense when I show the method. So encode, again, takes an A, maybe a string, and we're going to encode it. We're going to get a bit vector. Enc A is a bit vector. Then we're going to encode the size of that bit vector and get another bit vector. So size is a bit vector itself that represents how long enc A is in bits. And then we're going to add that bit vector together. So it's prefixed by the size in bits. Cool. So now we can make a var encoder. We're going to use uint8 and utf8. And we're going to encode h and hw. And then I'm going to just put these together and see what happens, right? So before we had, what, 16 bits for h and w? Well, it's a lot bigger now. It's double. So why is that? Does anyone know what like 0.8 represents? Right? It's the size of how long our string is going to be. So 68, right? Remember that's h. And then another 8 representing the next string. Cool. So now we need to make a decoder. Again, we're going to take the size for the codec and a val decoder. And that takes a bit vector. And the first thing it's going to do is it's going to decode the bit vector, and we're going to get a decode result. And we know that the first thing that it's giving us is the size, right? Because we have a size codec. So that's saying read this many bytes, whatever size bits of size dec is, and then we have a remainder. This is going to say we can take how much that is from the remaining bits and then we're going to decode that. We're going to put that in the value, and then we're going to drop the size from the remainder. So does that make sense? It's kind of ugly looking, but cool. So let's see if this works. So we have a decoder. We're going to pass in a uint8, UTF-8, decode byte vector from hex. So I only called the var decoder.decode once. What happened? We read the h because the first byte says how many bits to read. The next one is our 68. Is that right? No. And we have our leftover, which is the remaining, the size and the. I think that's my highlighting is wrong. It should be the 08 and the 77 is the leftover. All right, let's try it again. Sized UTF decoder. Sized UTF encoder. Now we want to make a sized UTF codec because we're going to go both ways. So codec has an apply. Oops, there's a typo, but hopefully you guys understand. I'm making a codec by passing in an encoder and a decoder, right? Remember, a codec just is both of those things. So now we have an actual codec for strings that's going to prefix the size of the string. User codec. All right, I'm going to need uint8 for the age, size codec, and a size codec. Cool. Ah, it looks more interesting now. So now we have those length, you guys can see we have those length prefixes in there. And when we round trip, as you see, it now knows how to read each part into the right spot of the tuple. So this is cool. We can now combine our little codecs, our primitive codecs, into more interesting codecs, and then just magically turn them into case classes. All right, I lied to you. You can't pass a uint8 into a size decoder and encoder. Did anyone notice why? The signature? No? All right, so how do we solve this problem? Right, our decoder requires a long, we want to require a long, right, for the type of the size. So what's decoder? If we can map on the attempt, when we map on the result, we can basically return a new decoder if we have a function a to b. Decoder is a functor. Cool. So we can now turn uint8 as decoder into a too long. What about the encoder? The A is the input. So is this a functor? It can't be, right? So look, if we have an F A to B, well, where do we're not returning the B, right? We're returning an attempt bit vector. So how do we encode this? Or how do we transform this? So we have a function called contramap on encoder. The function looks pretty similar to functor, or the map function, but if you look, B and the A are on the opposite sides. So I'm just going to return an encoder B. Encoder is a contravariant functor. The arrows are reversed. Or you could say the arrows are the same and the parameters are reversed. But it's the same thing. I'm taking input and transforming it before I feed it into my other input. So here's the encoding of the abstracted over contravariant. It's over anything over an F that has contramap. We'll take an F of A, a function B to A, and then we can return a B. So this is a contravariant functor. And it has laws. So anything that's a contravariant functor has to follow the composite laws. So if we have two functions, b to a and c to b, it's pretty similar to the functor associativity laws, right? I think that's right. Where we're making sure that when we contramap twice with these two different functions, it's equal to contramap composing the functions first and then contramapping after we compose them. Okay, what about codec? So is codec a functor? No. Is codec a contravariant functor? No. Because we have the decode, which returns an A, right? So we can't really just get a B to A because we don't know how to transform our attempt decode result back to A, right? There's two spots where the A is. It's on the left-hand side or the right-hand side. That's a bad way to look at it. It's input and it's output. So there's another type of functor called invariant. Here's the type class for an invariant functor. So this abstracts over an F. We have a function called xmap. Now xmap is typed to A and B. It takes an FA, and then it has two functions. An F that goes from a B to an A, and a G that goes from an A to a B. You can see how that probably makes sense when you have this codec that you want to turn into a B. So invariant has its own laws that are kind of gnarly, but it's pretty similar to all the other functor laws, right? We're just taking functions that go to A to B and B to A and B to C and C to B. We're making sure that when we xmap twice with the different functions, it's the same thing as when we xmap with the two functions composed going both ways. So why do I have all this information? Why do I care about codecs? So at Verizon, I have to sometimes deal with some weird protocols that nobody has implemented on the JVM. So I have to open up an RFC, and I have to look at all the bits in there, and then I have to write a way to spit out these bits and read these bits. Stun is an example that I recently had to do because there's apparently no good stun library open sourced for Java or Scala. So I wrote one. Stun is a pretty basic UDP protocol. It's for NAT traversal, if anyone knows about that. But it's not open source yet. I was trying. So I made another example. DNS. DNS is a pretty basic UDP request response protocol, right? We're going to send out a binary UDP packet and to a DNS server, and then the DNS server is going to say, or we're going to request a domain name, the IP of a domain name, and the response is going to be a DNS packet that has the IP address of that domain name. So what does that look like? All right, well, I had to go in the RFC and look at all this junk. You know, you see the bits lined up. And here's like the response. So you can see how I had to like go through all this, and there's a length of how much data there is, the TTL, all this mumbo jumbo. But I can kind of distill it down for our example to what a DNS packet is. And it has, I put this on my GitHub, so there's now a Scala DNS client. I don't know if anyone has ever wanted that, but you know, we have a transaction ID, a message type, a question, which is the DNS string that we're asking about, and a resource record, which is the responses, when there are responses, that say the IP of the question. So what's that like? So I made DNS string, which is a non-empty list, twitter.com, right? I have a class representing IP, which is just 4 ints. I have a class representing resource records, which is how long we want to keep this IP it's valid for. And then we have Scala's horrible, like, you know, enums for showing, you know, whether or not this is a request or response. Cool. All right, so I'm not going to do all the codecs, but especially because some of the codecs, I'm just ignoring a lot of the flags because I don't care. I want an example to show I can send a DNS packet out and we can get one back. But for an example, resource record, I'm going to ignore 64 bits because that's useless stuff that I'm not interested in. I have the TTL, and then I have IPv4. And again, this is just making this tuple and then casting, or not casting it, it's compile time generating is into the resource record class. And what's an IPv4 codec? It's a codec of 4 uint8 integers. And so you can see how we're kind of nesting these codecs inside other codecs, and it's going to give us a way to make DNS packets, etc., until we have codec DNS packet. All right. Now let's move on to NIO. So what's NIO? Non-blocking IO. You do this on the JVM. It's the idea that you're going to pass some data out, and you're passing a continuation, and it's going to non-blockingly invoke your continuation when there's actual data to be read, that sort of thing. All right, here's Netty. Netty client, blah, blah, blah. It's a whole bunch of junk that nobody cares about, right? I mean, it's important, but like at the end of the day, it's a callback for a client, right? We're passing in a function that takes the data that we get from the network, and we're getting back a function that lets us spit data out on the network. So let me explain this. So task, I don't know if anyone's from, I probably should have explained task. Think of task as just a context for saying I'm doing some side effecting in the real world. It's a monad. It just kind of shows that we're doing some side effecting here. Yeah?
Is this the Scala Z task?
It is the Scala Z task. But I mean, you could ignore it if you wanted to not be pure. You could have a delayed function or whatever. You could write IO. It doesn't really matter for this example. I was just being neat and clean. But you can see that I'm returning a task that I'm going to be able to run that gives me my function. So kind of our abstracted callback scenario for this processing of incoming data and outgoing data is what's going on. I'm passing in a function, a handler function, and I'm getting back a task that has a function in it. So my function that I pass in handles data coming in on the network. The return that that function that I'm getting is a task that has a function for sending data out on the network. And task unit is just kind of representing a side effecting call. So why did I switch the B and the A parameter though? Does anyone know? All right, I'll get to that. To turn a B unit to A to unit, I'm ignoring the task here. We need to transform or map both covariantly and contravariantly. So what kind of functor is this? All right, we finally got to it, right? You guys were waiting. So we know it's a profunctor. Why? So what's the signature of profunctor? It's going to abstract over something that has two type parameters. And it's going to have a method called dymap. Now you can derive some other methods from dymap, but this is the kind of the core thing you need. It's going to have 4 type parameters. What's happening? We're passing in our P, which is an AB, and then we're taking our C to A function. So that's a C to an A, and then a B to a D, and we're getting a P, C to D. So it's mapping both directions. It's functor plus contravariant functor, right? So remember how we had an A, if it's output, we have to take a to B, and if it's input, we need a C to A, right? So that's a profunctor. So what else is a profunctor? Function 1, right? I'm probably missing a bunch. So function 1, right, it has input, right? Let's say you have a function that takes an integer and returns an integer. There's input that you can transform and output you can transform. So it's a functor and a contrafunctor, also a profunctor. arrow. So arrow is kind of an abstraction over function 1, or actually lots of things. Kleisli. So if you guys are familiar with Kleisli from Scala Z, it's a function that around a context. So if you don't know what that is, it's not important. Index state is a profunctor, but if you don't know that, it's fine. Rconst, I think, is a profunctor. Forget is a really weird for profunctor, but there's a lot of profunctors. You start seeing them more and more. All right, so let's get back to this question of why do I have a B on the left and an A on the right? So what's my output here? This is the weird part. This is the kind of mind-bending part of my talk, so forgive me. But the output is the fact that I'm passing a function in that is going to take data, and I'm consuming the B, right? I'm not supplying the B, I'm consuming the B. And then when I get this, when I pass that function in, I'm getting a function that lets me produce the A and, you know, side effect or whatever. So it's the opposite of function 1 because my production is on the opposite side of my consumption. I could have made it A and B, but then it would be even more confusing, and I was really confused when I started writing the code. So it's a lot easier, in my opinion, to have the B on the one side and the A on the other. But it doesn't matter. It's just to help us understand which part we're mapping covariantly and which part we're mapping contravariantly. All right, that's kind of what I said. All right, when we have a profunctor of PAA, we can actually get an invariant functor. Remember, that's the one that I was talking about, that if you have an A, and if you take an B to A and an A to B, you can go from a FA to an FB. Same thing with profunctor. If your profunctor is PAA, you can go to PBB because you have those mappings on both sides. So you can actually derive the invariant functor class from profunctor when your profunctor is PAA. So our NIO call is a profunctor. In ways that A is the same as B, it's an invariant functor. Recap. Invariant functor has xmap, which takes a pair, A to B and B to A. So what else is a pair of functions? A to B and B to A. Does anyone know? Tony knows. Isomorphism. Cool. So let's look at ISO. All right. ISO is S and A. And we have S to get an A, and rget that we feed in an A, and we get an S. It's just a pair of functions. I mean, it could be a tuple of A to B and B to A, right? This is more interesting. We can compose ISOs. We kind of know this, but so if we have a way to get to from an S to an A, and we have a way to get from an A to a B, that means we can get from an S to a B, and it means we can go from a B to an S. And we can flip it, right? So these are some basic ideas on this concept called ISO. Well, the people who wrote Scala Z were really smart, and they came up with this, the fact that, you know, xmap I, which takes this function of B to A and A to B, you can just pass in an ISO. So that's useful. All right, so why was I talking about ISOs and why was I talking about codecs and all this stuff and neti and this idea of packets? It's because kind of using some of these libraries, we can start gluing stuff together, right? We can say that if we have an address and an array of a payload, we can make a packet. Like this is a datagram packet's like a UDP packet. It's a packet on the network. So it's where it's going or where it's come from in the address and a byte array to represent what our payload is. Right? We can always go back and forth. What else can we derive automagically? Well, remember, codec return does an attempt and a which is basically holding an error or a success for an A to a bit vector and a bit vector to an A. So we can derive an ISO from any codec that ends up being attempt A to attempt an attempt bit vector. But I don't like attempt, so I just made it into disjunction. Are you guys familiar with disjunction? It's either an error or it's an A. It's either a bit vector or it's an A. So we can derive an ISO from any codec. We can make an ISO for going from a bit vector to an array of bytes. We can make an ISO for a error of tuple inet socket address A to inet socket address bit vector. So I'm kind of just connecting these pretty simply. I'm kind of going far. So how do we get from an error bit vector with a composed with a bit vector to an array of byte? So ISO has this idea of strength. It's these two functions. Any function that's an A to B can become a C to A and a C to B. And that means that any B to A can become a C to B to B, yeah, C to A. So anytime we have an ISO between things that don't have a tuple, we can add the tuple. ISO also has an idea of this thing called choice. Any AB can become CA to CB, right? Hopefully that makes sense, because if we're passed in the error, we shuttle back the error. If we're passed in an A, we know how we can get the B. So here's our methods on ISO again. First, right, it gives us this tuple ISO. We can derive this tuple ISO. We can derive this choice ISO. So we can start gluing this codec with datagram packet, right? So I'm calling choice and write error compose with some of my other stuff. This is important to understand every single thing, but if you guys understand that we can kind of shuttle through this tuple like the inet socket address, and we can make things that don't have the error go to an error, and then that fits in with the things that expect an error. We can kind of just put everything together. All right. Yeah. Oh, okay.
In this context, error means a signal from the thing you're talking to, an intentional error, and the protocol is intact, or it means they sent you bad data.
Yeah, it means we couldn't decode the data in this sense. So does that make sense a little bit? All right, cool. And then so write choice is kind of we can always signal that even though we weren't planning on handling error, we're going to support handling an error for this ISO, going back and forth. All right, so I don't know if anyone believes me, so let's go to the more interesting stuff. Is it pretty tiny? Do I need to make it bigger? Yeah. All right, I'm going to see if I can write a DNS client from scratch, right? This is my crazy part of the talk. That was probably a terrible idea, but you guys are stuck here. Well, not really, but. So I'm going to import my load of stuff that I need. Let's make a request. So I'm going to make a request. We have kind of this, this is my DNS class to hold the data. All right, I have an ISO that takes a codec to bytes, and you just need to implicitly, it's going to implicitly grab the codec. So did I grab that? So we have our ISO on our. Now I made this netty handler. That's the thing that I talked about that basically wraps this netty plumbing into a continuation passing function that takes our stuff. And remember, that's a profunctor. I kind of skipped this part. It's actually a choice profunctor, so I can do the choice right again as I was talking about. So here's where I'm actually going to start. Cool. We need to derive an invariant functor, right? And dot x map I. We have our f iso. Nope, I did the wrong thing. Oops. Sorry, I'm gonna have to debug this, but we will have a DNS client in a few minutes. Oh, I see. F.f. No? And a function one. DNS packet. Sorry, guys. I'll give myself a couple more minutes before I scroll through my history and see what happens. So. Oh, I didn't say what that. I think it's the inference that's dying. Ah, okay. I see what I did wrong. No. Well, I'm going to keep working on this. Sorry, guys. Well, I'll take questions first, and then I'll finish this up. If anyone has any questions, but it'll probably take me 4 more minutes. But yeah.
In a language without H-lists, would you recommend using an implicative functor to do the similar the S-codec style thing?
I mean, instead of doing it magically, you could just like make a custom codec that and uses the codecs in the for comprehension to create like your case class directly. So maybe you could, but you don't have to use the H-list way to do it. Like kind of like how I was making my Var encoder. You can construct like a complicated codec like that.
Right. I guess it would be a moment.
Yeah. So in.
Language doesn't have H-list. You should write.
Any other questions or?
Switch that. Yeah, I'm thinking Max would have written that.
Maybe I have it written somewhere else. Other questions or? Yeah.
Are there examples of profunctors without string? It feels so intuitive, but that one
I don't know actually. Do you know, Tony? I can't think of any that don't have strength.
Usually, most programming languages, all factors have a strength. So,
All of them have strength?
yeah, like, I don't know for Scala, but then for Haskell, essentially have a strength because how the language is.
But one of the Profunctor objects doesn't have
They don't require strength, but I'm...
No, I think you're asking, is there an instance of Profunctor but not strength?
Yeah.
Yeah, I don't know, off the top of my head.
All right, well, I'm going to keep working on this, but that's all I have. If anyone wants to wait 5 minutes, I may have a working DNS client for playing around with, but that's my talk right now. So thanks, guys.
High density. High density.
Oh, I don't know why it worked.
You get a source?
I think so.
I want to see a DNS client.
Oops. I didn't. Cool. So this really is from scratch, except I wrote all the codec. But yeah, there you see it. So this, I sent a packet and I got back the a ton of IPs for this. I called the whatever the school's DNS was. I looked it up. So yeah, we have a DNS client. You just need to figure out the way to merge the codecs with the ISOs with the neti abstraction. So it took a little bit of funging with the Scala inference.
Now I have a question.
Yeah.
So I deal with a decoding problem. It's a little bit different because I have a stream of data.
Yeah.
There's no packets.
Oh, okay.
So if you get an error, you don't know where you're at. So the error handling has to include synchronization and things like that. So we always use state machines because we can always like say, if nothing's happening, print for a long period of time, reset, look for.
Yeah.
Do you think that this could be adapted to handle?
I mean,
or
yeah.
you always have like a packet marker to say, I know where I start.
Yeah, I think you want. I don't think you want a codec. I think you want like a parser, right? Yeah.
Something like a parser.
Yeah, because then because then that parser is like a state machine that can kind of
Yeah, the problem with the state machine is it's not. You can't build a little language of pieces to compose, right? It's hard to make it complicated. I mean, it's not completely impossible, but it's harder. It's hard to make it a state machine. Maybe I actually just don't know how to do that.
Yeah.
Maybe there's a way.
Yeah, I don't know. That's interesting. It's an interesting problem.
Maybe a state pattern could be.
All right, cool. So yeah, man, this is the type inference, and
What's that?
I was just.
Oh, is that all it was? I wasn't watching.
Well, no, I mean, yeah, that was throwing me off. It was giving me, yeah, but they only needed a few.